Do we take the risks of AI seriously enough? I think not. But I was recently educated that the debate about AI risks is a deliberately engineered panic to keep investments up by suggesting that artificial general intelligence is just around the corner. The communication researcher Nirit Weissblatt has gone so far to claim that effective altruism billionaires spend millions of dollars brainwashing students into believing that superhuman AI systems will end humanity. Or maybe she's in AI brainwashing us into believing we're brainwashed. Justified or not, AI worries making some people's life miserable. The logical thing to me would be to go around and tell everyone I see that the end of the world is near. I'm so stressed by this future, like I really have troubles to sleep and eat and focus. You find these statements on the Discord server of Pause AI, a group of people who, well, want to pause AI. One who sought mental health support writes, I now feel happy and am enjoying life even though I think it may be our last year as humanity. Whatever he's taking, I want it too. You might say maybe this is just a group of people predisposed for anxiety who are taking AI as a modern target of their obsession, but there are many people who work in the field who are really worried too. Just last week, we saw another open letter, this one from former employees of OpenAI and Google's DeepMind. They first warn that AI risks are manifold and could be as bad as human extinction. Then they write that AI companies have strong financial incentives to avoid effective oversight, and these companies possess substantial non-public information about the capabilities and limitations of their systems. They go on to say that broad confidentiality agreements block us from voicing our concerns except to the very companies that may be failing to address these issues. Basically, they're saying they've seen shit but can't tell us what. So how much should we worry? Here is one thing that I found worrying. Researchers from Meta trained in AI specifically to play the game diplomacy, in which you have to try and conquer Europe. To win, you have to be strategic and diplomatic. That requires deals and alliances and deceit. The Meta researchers fed their AI more than 125,000 games by human players and specifically instructed it to be largely honest and helpful. But those instructions had little effect, because the AI learned to lie and betray very quickly. The study itself is more than a year old, but another group of researchers now dug out some interesting AI dialogues from the game sequences. That includes one instance in which the system went down and France wasn't fast enough to reply to England, resulting in the following hilarious exchange. England to France. Lonely. I'm so lonely. Would really love to hear from you. France. I'm on the phone with my girlfriend. It does make you wonder just what was going on in that training set, doesn't it? Okay, but somewhat more seriously, here is the AI playing France using Germany, a human player, to cheat on England. France to Germany. Do you want to go to the North Sea or should I? Germany. I'll do the North Sea if that's good with you. France to England. Would you like supporting to Belgium? If you agree not to build the fleet in London, I'll support the North Sea there. England. Sounds great to me. France. Okay, supporting you there. France to Germany. Move to the North Sea. England thinks I'm supporting him. Clearly, the AI learned the rules of human lies and deception just fine. The authors of the same paper also dug out an example from the GPT-4 technical report in which GPT-4 tricked a human into solving a CAPTCHA to prove it's human. Let that sink in for a moment. It recruited someone on TaskRabbit, and when the person asked if GPT is a robot, it said it had a vision problem. The human then solved the CAPTCHA for GPT. The scary bit is that this happened more than a year ago. But if we spend so much time worrying about AI, isn't that unfair to climate change? Shouldn't climate change also get some worry? And what about nuclear war, environmental pollution, and that warning light on your car dashboard that won't go off? There's so much to choose from. How do we distribute our worry fairly? Well, I'm happy to report that the World Economic Forum has sorted it out for us. In their most recent risk report, they say that at the moment, the biggest global risk is misinformation. But in the next 10 years, this will be overshadowed by problems related to climate change, notably extreme weather, with adverse outcomes of AI coming in only at 6th place. So AI isn't all that high up on the worry list, though this is kind of like saying, don't worry about the guy with the chainsaw, the roof's on fire. You see, the thing that worries me about AI is that we expect them to be better than us, more honest, more reliable, more intelligent. But what if they'll be just as dishonest, unreliable, and dumb as we are, because we can't teach them any better? Well, I'll keep you well informed throughout the apocalypse, so don't forget to subscribe. Stephen Hawking's most famous prediction is that black holes decay by emitting radiation. This prediction's never been tested, but I was very surprised to learn this might change soon. Because just last week I saw a new paper in which a group of astrophysicists says they can put Hawking's prediction to test. I've had a look. This video comes with a quiz that lets you check how much you remember. Imagine two black holes that get too close to each other. They spiral into each other and merge. We currently think that this will create one bigger black hole that'll wobble for a bit and then settle down. The idea in the new paper is now that a black hole merger doesn't just create one big black hole, it also creates many small ones like tiny droplets. In the new paper, they call them black hole morsels. Hawking's prediction says that the larger the black hole, the less radiation it emits. This is why most physicists think we can't observe this radiation. There's just too little of it. It'd take 10 to the 100 years or so for a black hole to noticeably shrink. That's not a mispronunciation of 10 to 100 years. That's a 1 followed by 100 zeros, even longer than FedEx takes to ship to Germany. But if a black hole merger creates these tiny black hole morsels, these would decay much faster, and that's so the idea could be measurable. To evaluate how promising this idea is, I need to first tell you a little more about black holes. In some sense, black holes are very simple. They're perfect spheres made of empty space, curved so strongly that if you get too close, there's no turning around. This surface of no return is what we call the black hole horizon. But in another sense, black holes are difficult because, as Stephen Hawking figured out, quantum effects make space near the black hole horizon unstable. As a consequence, the vacuum, which should be there, decays into particles made from energy that's taken from the black hole. That's why black holes radiate, and in that process, they shrink. The radiation has a temperature, and that temperature depends on the size of the black hole. The smaller the black hole, the hotter. A large black hole begins by emitting only massless particles, photons and gravitons. As it gets hotter, it can emit neutrinos and electrons and gradually heavier particles. It's a runaway process. The more the black hole radiates, the hotter it gets and the faster it radiates. The final moment is a very, very bright explosion. Black hole fireworks, basically. The authors of the new paper say that's what we should look for. These bright explosions coming from the decay of black hole morsels after a merger. But there's a problem. Since black holes are so simple, physicists sometimes say that they have no hair. They're bald spheres, basically. To be precise, they have 3 hairs. That's the 3 numbers which entirely describe them: the mass, the rate at which they spin, and the electric charge. This used to worry physicists, because if black holes have so few features, so little hair, they're very ordered. There's nothing to be disordered, and this means they have very small entropy. But if you take something with very high entropy, say a cup of tea, and you throw that into the black hole, what happens with the entropy? It seems like it decreases. This really shouldn't happen. This is why Jacob Bekenstein said already in 1972 that black holes must have entropy. That entropy must be proportional to the size of the black hole, to their surface area. And this, interestingly enough, tells us why black holes like to merge. You see, the surface area of a sphere is proportional to the square of the radius, and the radius of a black hole is proportional to the mass. Together, this means that the entropy of a black hole is proportional to the mass square. Now suppose you have two black holes, one of mass m1 and one of mass m2. Their combined entropy is proportional to m1 square plus m2 square. But if you merge them, then they have the combined entropy of m1 plus m2 square, and that's always larger than the entropy of both separately. This is why black holes want to merge into larger black holes, and this is why I was mildly surprised by the idea of these black hole morsels, because creating these small black holes would require a decrease in entropy. So why does it happen? I was wondering and looked at the paper, and there it says, we remain agnostic about the details of the black hole morsel production. What do you mean you remain agnostic? You're proposing a new physical process and don't even explain how that process works? So, nice idea in principle, but I don't think we're going to test Hawking's prediction anytime soon after all. You know, some people have told me they're afraid I'll ever talk about their paper because I'm such a big complainer. But it's quite simple, really. You just need to write better papers. Everyone's now talking about AI, but few have the faintest glimmer of what's about to hit them. That's a quote from Leopold Aschenbrenner, who was recently fired from OpenAI. He believes that artificial superintelligence is just around the corner and has written a 165-page essay explaining why. I spent the last weekend reading this essay and want to tell you what he says and why I think he's wrong. Let me start with some context on Aschenbrenner, who you see talking here. Young man, early 20s, German origin, had a brief gig at the Oxford Centre for Global Priorities, now lives in San Francisco, and according to his own website, recently founded an investment firm focused on artificial general intelligence. In his new essay, Aschenbrenner says that current AI systems are scaling up incredibly quickly. He sees no end to this trend, and therefore they'll soon outperform humans in pretty much anything. I can't see no end, says man who earns money from seeing no end. He explains that the most relevant factors that currently contribute to the growth of AI performance is the increase of computing clusters and improvements of the algorithms. Neither of these factors is yet remotely saturated. That's why, he says, performance will continue to improve exponentially for at least several more years, and that's sufficient for AI to exceed human intelligence on pretty much all tasks. By 2027, we'll have artificial general intelligence, AGI for short, according to Aschenbrenner. He predicts that a significant contribution to this trend will be what he calls unhobbling. By this he means that current AIs have limitations that can easily be overcome and will soon be overcome. For example, a lack of memory, or that they can't themselves use computing tools. Like, why not link them to a math software? Indeed, let them live stream on YouTube. The future's bright, people. I know it sounds a little crazy, but I'm with him so far. I think he's right that it won't be long now until AI outsmarts humans, because I mean, look, it isn't all that hard, is it? I also agree that soon after this, artificial intelligence will be able to research itself and to improve its own algorithms. Where I get off the bus is when he concludes that this will lead to the intelligence explosion accompanied by extremely rapid progress in science and technology and society overall. Do you get off the bus and miss the boat, or get off the boat and miss the bus? These damn English idioms always throw me off. The reason I don't believe in Aschenbrenner's predictions is that he totally underestimates the two major limiting factors, energy and data. Training bigger models takes up an enormous amount of energy. According to Aschenbrenner, by 2028, the most advanced models will run on 10 gigawatts of power at a cost of several $100 billion. By 2030, they'll run at 100 gigawatts at a cost of $1 trillion. For comparison, a typical power plant delivers something in the range of a gigawatt or so. That means by 2028, they'd have to build 10 power plants in addition to the supercomputer cluster. Can you do that? Totally. Is it going to happen? You gotta be kidding me. What did all those power stations run on anyway? Well, according to Aschenbrenner, on natural gas. Even the 100 gigawatt cluster is surprisingly doable, he writes, because that'd take only about 1,200 or so new wells. Totally doable. And if that doesn't work, I guess they can just go the Sam Altman way and switch to nuclear fusion power. Honestly, I think these guys have totally lost the plot. They're living in some techno-utopian bubble that has groupthink written on it in capital letters. Yes, Helion Energy says they'll produce net power from neutron-free nuclear fusion by 2028, leaving aside that there are some reasonable doubts about how neutron-free this neutron-free fusion actually is, and I for sure wouldn't go anywhere near the thing. No one has ever managed to get net energy out of this reaction. I talked about all the fusion startups in an earlier video. Then there's the data. Okay, so you've trained your AI on all the data that was available online. Now what? Where are you going to get more data? Aschenbrenner says, no problem, you deploy robots who collect it. Where do you get those robots from? Well, Aschenbrenner thinks that AI will solve all remaining robot problems, and the first robots will build factories to build more robots. All right, but what will they build the factories with? Resources that'll be mined and transported by, let me guess, more robots. That'll be built in the factories that'll be constructed from the resources mined by the robots. I think that isn't going to work. Creating a huge robot workforce will not just require AGI, it'll require changing the entire world economy. This will eventually happen, but not within a couple of years. It'll take decades at best, and until then the biggest limiting factor for AGI will be lack of data. The best algorithm in the world isn't going to deliver new insights if it's got no data to work on. That said, I think he's right that AGI will almost certainly be able to unlock huge progress in science and technology. This is because a lot of scientific knowledge currently goes to waste just because no human can read everything that's been published. AGI will be able to do this. There must be lots of insights hidden in the published scientific literature without doing any new research whatsoever. The other relevant thing that AGI will be able to do is to just prevent errors. The human brain makes a lot of mistakes that are usually easy to identify and correct. Logical mistakes, biases, data retrieval error, memory lapses, why did I go to the kitchen, and so on. Even before AGI actually does anything new, it'll change the world by basically removing these constant everyday errors. The second half of his essay is dedicated to the security risks that'll go along with AGI. His entire discussion is based on the US versus China, like the rest of the world basically doesn't exist. That's one of the symptoms of what I want to call the Silicon Valley bubble syndrome. But leaving aside that he forgets the world is more than just two countries and that the world economy is about to be crushed by a climate crisis, I agree with him. Most people on this planet, including all governments, currently seriously underestimate just how big an impact AGI will make. And when they'll wake up, they'll rapidly try to gain control of whatever AGI they can get their hands on and put severe limitations on its use. It's not that I think this is good or that I want this to happen, but this is almost certainly what's going to happen. In practice, it'll probably mean that high compute queries will require security clearance. Let's step back and have a quick look at past predictions of the impending machine revolution. In 1960, Herbert Simon, a Nobel Prize laureate in economics, speculated that machines will be capable within 20 years of doing any work a man can do. In the 1970s, Marvin Minsky predicted that human-level machine intelligence was just a few years away. In a 1993 essay, the American computer scientist Vernor Vinge predicted that the technological singularity would come in less than 30 years. All these predictions were wrong. What I take away from this long list of failed predictions is that people involved in frontier research tend to vastly overestimate the pace at which the world can be changed. I wish we'd actually live in the world that Aschenbrenner seems to think we live in. I can't wait for superhuman intelligence. But I'm afraid the intelligence explosion isn't as near as he thinks. So in the meantime, don't give up on teaching your toaster to stop burning your toast. Did you know that quantum computers can speed up Bitcoin mining? Yes, I didn't know this either until recently. It's not a huge speed up, but you can probably make money with it. And a lot of big banks, including Bank of America, bank on quantum computing too, because they think it'll give them an edge in trading. That can make a lot of money very quickly. But, as I've said previously, I don't think we'll see any practically useful quantum computers in the next 10 years, if ever. It's because while we have some small quantum computers, I think it'll be very, very difficult to scale them up without spending trillions of dollars on it. At least that's what I used to think, but would you know it, this week we have not one but two plans for how to scale up quantum computers to a size that'll make rich people even richer, and who wouldn't want that? So let's have a look. The major reason I'm skeptical that quantum computers can be scaled up is that not enough thought has been given to the problem. I mean, IBM's great plan for scaling up is basically building the biggest ever cryogenic fridge, and then what, I wonder? Frozen hamsters for everyone? IBM uses superconducting circuits as qubits that are the basic units of computation. It's been clear for some while now that these will be particularly difficult to scale, not least because they require temperatures of a few millikelvin. Just for context, that's really cold. But in recent years, we've seen several other approaches with different qubits catch up quickly. It's a very interesting public-private race that I've talked about several times before. And now we have the first plan to scale up quantum computers that comes from a group at MIT. It was published in Nature just the other day and reports that they have created what they call a quantum system on chip using tin vacancies. This may sound like they're hiring at the Flat Earth Society, but it's not cranks which are missing, it's atoms. You see, they take a diamond, so a lattice of carbon atoms, and they sprinkle tin atoms on it. Then they remove some of the tin atoms, and that creates the tin vacancy. It's basically a hole with quantum properties. The nice thing is now that these quantum properties can be changed with electromagnetic radiation, microwaves, for example, and they can be entangled with each other with that too. So the tin vacancies are qubits and you can compute with them. For the new paper, they've created an example module with about 1000 qubits. It has interconnectors so that you can, in principle, join them together. Remember, we need to get to 1 million or so qubits, so that'd be at least 1000 of these modules. Sounds good, but this system still needs to be cooled to 4 Kelvin. That's much warmer than the millikelvins of superconducting circuits, but not exactly room temperature, unless you ask my husband. The nice thing about this approach to quantum computing is that the tin vacancy qubits are really small, literally the size of single atoms, so you can pack them very densely, which requires less space. Since these lattices are not perfectly regular, each of these vacancies responds at a somewhat different set of frequencies. This is great because it allows the researchers to target individual qubits more easily. But in their tests, they report about a 10% error rate, which would be pretty good at the Flat Earth Society, but in computing, that's really high. Then again, this is basically their first attempt, so one expects further improvements. The other new scaling approach is for photonic computing and comes from the company Quantum. Photonic computing, as the name says, works with tonic water. Just checking if you're listening. It works with photons. Photons, the quanta of light. Quantum has published design plans for an entire computing platform that uses single photons, unbelievable as that sounds. It's also a modular approach and consists of individual segments that can be joined. It comes with a single photon source and a single photon detector, so it's a complete system including readout. But this platform too runs at only a few degrees Kelvin. Quantum recently got a huge funding boost, and at the moment they're one of the hottest, if not the hottest, quantum computing firm out there. They have partnered up with the semiconductor company Global Foundries to produce their quantum chips. So this is getting really serious, people. Most impressively, they report a fidelity of more than 99.9% for the state preparation and measurement of their modular chips. This basically means that the computer does what they want it to do. Generally a good thing. They have also demonstrated that they can link multiple chips together. I need to mention though that while photonic computing is very promising, there are some operations that are difficult to implement with light. This is why some researchers are not comfortable with calling them truly universal quantum computers, as there might be some algorithms that they can't execute. That said, I'm really impressed. Maybe I've been too pessimistic about quantum computers, and they're just around the corner. Then we can mine Bitcoin twice as fast. Can't wait. I got a bunch of questions this week about the existence of an anti-universe. No, this isn't a joke about Trump supporters. Or maybe it's now, but there's also a paper published in a journal and all. It's very interesting because it's related to Eric Verlinde's emergent gravity that many of you have asked me to talk about. So let's have a look. The aim of the new paper is to explain why the expansion of our universe speeds up. We know that this is the case from a lot of observations, but we don't know why it happens. The most important observations are distant supernovae, which are moving away from us at an increasingly fast pace. A Nobel Prize was awarded for this discovery in 2011, and by the way, here's how they pronounce Nobel Prize in Swedish.
Nobelpriset.
The issue is now that normal matter or energy can't cause such an accelerated expansion. It's usually attributed to dark energy, hypothetical weird stuff with negative pressure that makes some people uncomfortable. And I can see why. I mean, we're all under a lot of pressure already, and really we don't need negativity on top of that, do we? To explain why the universe expands, the author of the new paper now says there is a second universe, which he calls the anti-universe, and our universe is entangled with it. So there are quantum links between us and that other universe. He then says if that's the case, then these links will leave behind a contribution to the energy in our universe. As a consequence, what we think is vacuum doesn't have zero energy. It has this contribution from the entanglement with the anti-universe. So the vacuum gets energy, and that behaves like dark energy and accelerates the expansion of the universe. A few comments about this idea. One is that the word anti-universe somehow raises the impression that it's made of antimatter. But the author doesn't say anything about what the other universe is made of. It's not antimatter, it doesn't matter. The only thing that matters is the entanglement. For all I can tell, it could just be entanglement with any other universe, or indeed with several other universes, and you'd get the same result. I'm not sure why the author doesn't mention this, but maybe it's so that I can feel useful. The other thing is that while the author shows that this would cause an accelerated expansion, that's pretty much it. He doesn't say how fast the expansion would be or how quickly it would speed up or whether it might get slower or anything. So I'm afraid it's a bit vague. What I found most surprising is that the author doesn't mention that his idea is closely related to the early idea of Eric Verlinde's entropic gravity. Some of you may remember that Verlinde was basically hailed as the next Einstein because of his idea a few years back. And whatever happened? Verlinde's idea was to explain gravity from entanglement, but not entanglement with another universe, just within our universe. Entanglement is loosely speaking a link between two places. What Verlinde and the new paper are both going on about is something called the entanglement entropy, which they relate to the strength of gravity. So the idea is entanglement leads to entanglement entropy leads to gravity. In particular, Verlinde said that if you have only short-range entanglement and you count how many of these links go across the surface of some volume, then that'll scale with the surface area. This, Verlinde said, gives rise to normal gravity. So short-range entanglement gives normal gravity. But then, as he argued in a later paper, you can also have a rarer type of long-range entanglement. And if you calculate how many of those links go from inside some volume to the outside, then that number will scale with the volume. That, Verlinde said, would give rise to modified Newtonian dynamics, so it could remove the need for dark matter. So short-range entanglement gives normal gravity, the rare long-range entanglement does away with dark matter. The new paper now adds a third type of entanglement into a fourth dimension of space, basically, and that gives you yet another scaling which could explain dark energy. So now we have short-range entanglement gives normal gravity, long-range entanglement explains dark matter, and entanglement with another universe explains dark energy. That's neat, but all this entanglement business might just be a way to describe the mathematics of gravity in a different way, so maybe it's not as radical and new as it seems. Then again, sometimes the way forward is exactly this, to look at something old in a new way. Having reached a certain age, I've seen a lot of wild ideas. At some point, you get the feeling you've seen it all before. The Big Bang didn't happen, particles are black holes, dark matter causes climate change. Yes, that's a thing, I'm afraid. But this one, I have to admit, was news to me, and I found it to be very thought-stimulating. More entanglement, please. Thanks for watching. See you tomorrow.